Last time we continued talking about the heat capacity of solids, and we made the argument that what really matters for determining whether a mode freezes out is this ratio of kBt to the quantum level spacing. So if that ratio is large, meaning kBt is comparable to or greater than the quantum level spacing, then it's relatively easy for the system to be promoted out of the ground state. And so that term will contribute strongly to the heat capacity. Whereas if this ratio kBt over delta E is small, then the system is almost always in the ground state, and you get very little contribution to that from that term in the total energy to the heat capacity. So basically, if you increase delta E, you're going to move to the right on this. If you decrease it or equivalent, when you increase delta E, you're going to move to the left on this. If you decrease it or equivalently increase the temperature, you're going to move to the right. We talked about how we're going to show either tomorrow or probably on Friday that when you're talking about a mass vibrating in a spring, the angular frequency of vibration is K over M. So if you have a hard material, that means a large value of K. That gives you a big omega. Or if you have a small m, that also gives you a big omega. Both of those give you a large quantum level spacing. And that's going to mean at room temperature that the vibrations are mostly frozen out. So you get a lower heat capacity. Then we just started talking about CV versus CP, the heat capacity constant volume versus that at constant pressure. So we're comparing these two systems. One where there's a piston that can move up and down, and one that's in a box of fixed volume. So when we add the same amount of heat to both of these, in this case, the piston is going to move upward as the gas gets hotter. And so some of the heat that we put into it goes into the work that's done against the piston. Whereas here, all of the heat goes into raising the temperature of the gas. So we're in the midst of computing the work that's done against the piston, and using the ideal gas law, we showed that dW equals nR dt last time, but we're not quite done using this to find what CP is. So questions about any of that? Okay, I also want to let you know, so next week we have our final exam. Pretty sure that the format is going to be similar to the exams that you've had previously. I'll make a final announcement about that soon. This will be a cumulative final, so there will be some questions that are specifically on the material that we covered in the first third of the class, and some on the second third, but most of it will be on what's been, or not most of it, there will be extra emphasis on the material that's covered since exam 2, since you've not previously been tested on that. I'm going to send out a poll to you guys later today about whether we should make the final exam closed book or not. There are some disadvantages to making it closed book, and I'll try to enumerate those in the poll. So for right now, and also towards the end of this week, I will, as I've done before, put up a list of topics and some practice questions. And we will have optional meetings next Monday at our normal times, during which we'll have the Q&A sessions that we usually have before each exam, but again, those are optional. So any questions at this point about the final exam?
Will the final exam be approximately the same length, or will it be longer?
It will be longer, so it will probably be 3 hours, maybe 3.5. Okay, so let's finish up our discussion of CP versus CV. So again, in this case with the piston, first let's talk about why is that actually a constant pressure case. So if we drew a free body diagram for the piston looks like this. It has its weight pulling down on it, and it has the force from the gas, which is the pressure times the area of the piston. pushing up on it. And if it's not moving, those two are constant. So even as it moves up and down, those two forces are going to balance as long as it's moving up and down slowly or at constant speed. And so therefore, PA equals mg, and so the pressure has to be constant. So pressure equals mg divided by A is constant. Okay. But as we said last time, some of this heat goes into pushing the piston up, some goes into heating up the gas. So we could write that as dq, a small amount of heat that we put in. Part of it goes into the work that we just calculated, pushing the piston up, and part of it goes into the thermal energy of the gas. So if we substitute in our expression for dW that we got last time, that was nR dt. So dq equals nR dt plus du. And then to get the heat capacity, we just divide or multiply both sides by 1 over dt. So on the left side, we have dq by dt equals nR plus du by dt. So this is just the heat capacity, and we're working at constant pressure, so we could write it as P. du by dt, that's what we'd get for this example, where all the heat is going into the gas. So if this dW term was 0, we just have the du term. So that's what we already calculated. That's the heat capacity at constant volume. And so what we just showed is that for an ideal gas, heat capacity at constant pressure is equal to little nR plus the heat capacity at constant volume. And if we're talking about the molar heat capacity, N is the number of moles. So for the molar heat capacity, little n would be 1. So Cp molar is just R plus Cv. So that's, this is for ideal gas. That's a pretty significant difference between the heat capacity at constant pressure and the heat capacity at constant volume. Say, for example, for a monatomic gas, we showed that the heat capacity at constant volume was 3/2 R. So the heat capacity at constant pressure would be 5/2 R. That's rather different. Questions?
At the beginning, when you talked about the piston, is the area the area of the container?
It's the cross-sectional area of the piston. So if we're looking here, it's also the cross-sectional area of the container because they have to match so the piston can make a good seal. So it's like that. Yeah. Other questions? Okay, so now I'm going to ask you a concept test to see how well this stuff has registered. But I want to, last time we talked briefly about thermal expansion, so I just want to hit that just a little bit more before I ask this concept test, that when solids and liquids are heated, they expand, but not very much, not as much as gases, but only slightly. So I should have looked this up. I'll look it up during the concept test, but it's a very small amount. So let's say for a typical temperature change, it's going to be much less than 1% of expansion, whereas for a gas, when you heat it up, it could expand quite a bit. So given that, I want you to consider the ratio Cp minus Cv divided by Cv. And these are all we're thinking about molar heat capacities. And is this for a solid greater than, less than, equal to, or can't tell that ratio for a monatomic gas? And I want you to assume the high temperature limit in both cases. So again, the way that you would measure the heat capacity is you put some energy, thermal energy in, and you measure the resulting change in temperature. So if you're going to measure that at constant pressure for a solid, you'd have this block of solid, in the air, which is constant 1 atmospheric pressure, you'd put some thermal energy in and you'd allow the solid to expand, you measure how much its temperature goes up. If you want to measure it at constant volume, you'd sort of somehow put it in a vise to keep it from expanding and repeat that experiment. Are there any questions about the concept test before I assign you to your breakout rooms? Okay, excuse me. Okay, I think we're all back. So you guys have a tendency, and I understand it, that you want to have an equation to solve. And I'm sort of trying as much as I can over the course of this semester to develop, in addition to that, which is an important way of thinking, to have you be able to think more intuitively and qualitatively. And that's the way that we need to approach a problem like this. So Phoebe, do you want to walk us through this?
So I did use the equation that we had for the ideal gas to get an answer for a monatomic gas.
Okay, let's do that part first.
So setting Cp equal to R plus Cv, and then if you subtract the Cv from that, you just get R. And for a monatomic gas, the heat capacity is 3/2 R. So you get R over 3/2 R, which is 2/3. And then, I mean, you don't have an equation for a solid. We do know that the heat capacity constant volume is 3R, so I just wanted to keep that in mind. And then you know that the work that goes into expansion, because the Q that you add is going to be the same for both, but more work is going to go into expansion for the gas than with the solid.
Okay, can you spin that out a little bit? Why is this smaller for solid?
Because the solids expand less than gas when they're heated. They only expand slightly.
Another way of saying that is dW equals F times dx, and the dx is small for a solid. Good, go ahead.
Yeah, so that's kind of as far as I'm at right now.
No, that's good. That's good. So can somebody else pick it up from there? What does that mean about the ratio, or what does that mean about Cp compared to Cv for a solid? Are they going to be really different from each other, or really similar? So what we're saying is that for a solid, almost all this dq goes into du. Quite a small amount goes into dw because the amount of expansion is so small. So what does that mean about the comparison between Cp and Cv for a solid?
They're like similar to each other.
Yes. So if dW, in the case of constant volume, dW would be exactly 0. And so then dq equals du, and that's constant volume. If dW is small, that means Cp will be a little bit different, but not nearly as different as for gas. So that means that Cp is approximately equal to Cv for a solid. And Sydney, what does that mean about the ratio Cp minus Cv over Cv for a solid? That's about equal to what?
0.
0, which is much less than 2/3. Good. Questions? Okay. So we're going to set that aside, and we are going to talk some more about gases. But before we do that, we need to sort of be ready for the next part of our conversation. We need an important aside, which is terminal velocity. And this will set us up to finish our discussion of gases. So because of some of the material that we had to make optional, we haven't talked much about air resistance in this class, but I just want to give you some of the highlights right now. So let's say you're skydiving and you jump out of the airplane. At first, when your velocity is quite small, you hardly feel the air resistance at all. So basically, there is a force mg acting on you. But as you fall, you start to gain speed. So here you are, you're falling faster, you've got a bigger velocity now. And you guys all know that you will feel a force of air resistance. You felt this if you go running, or if you stick your hand out the car of a window, you feel a force pushing you backwards. And so the faster you fall, the more that force is going to build up on you. And eventually it's going to build up to the point where it's just as strong as the force of gravity down on you. And so at this point, there's no net force on you. And so you continue to fall, but at a constant speed. So the force of air resistance increases with your velocity. And so now when these are balanced, we call your speed the terminal velocity. Let's talk just a little bit more about the force of air resistance. For small objects and low velocities, the force of the air resistance turns out to be proportional to the velocity. For larger objects and or higher speed, the force turns out to be proportional to v squared. So, and this transition from air resistance proportional to v to air resistance proportional to v squared occurs when we get the onset of turbulence. So if you imagine moving your hand through the air very slowly at a speed of just sort of several centimeters per second, you can imagine that the air can kind of move smoothly around your hand. That's the non-turbulent limit. Whereas if you move it quickly, there's all kinds of vortices that are created behind your hand, so that's turbulence. So most of our human experience is in this limit. So most of the time when we're moving around typical human-sized objects, we're creating turbulence, and the air resistance is proportional to v squared. However, for microscopic organisms, all their experience is all in this other limit of non-turbulent air resistance or water resistance as well, same thing, or same physics. So they're always in the limit where the force is proportional to the velocity. Questions so far? Okay. So let's think about what this feels like when you jump out of an airplane. So first, I want to consider the way things feel when you're just standing on the ground. Standing on the ground, of course, you've got the force of gravity working downward on you, and the normal force is canceling that out. It's of equal magnitude. And I want to think about the force on your liver or some other internal organ when you're standing on the ground. So it has its own gravitational force, little mg acting downward, and there are tendons and other things inside of you that are pulling up on it so that it has net zero force acting on it. That's what feels normal to you. You are used to this feeling of the tendons that are supporting your internal organs having some tension in them, pulling the organs up. When you first jump out of the airplane, now you have an unbalanced force acting on you. The only force acting on you is the gravitational acceleration. So all of your organs are also, they're accelerating at the same rate. So here's your liver. It also only has that force mg. There is no tension, t equals 0, acting up, because we need to have the liver accelerating at the same rate as the rest of your body. So you feel no tension on the ligaments, and that's what makes it feel strange to you when you jump out of an airplane. Maybe you haven't. Has anybody here gone skydiving? Ariana, you have. Oh, and Marissa, cool. So you have experienced this, but the rest of us probably have only experienced this in like a roller coaster. When you get up to the top of the first hill and you start going down that first steep incline, you feel kind of funny in your stomach, in your belly. And the reason is that you're not experiencing the normal tension that you do because all your organs are sort of in free fall. But when you're at terminal velocity, now it's different. Now you're falling down, you've got your weight force here, but it's being countered by the air resistance. So you're no longer accelerating. And similarly, your liver had better not be accelerating either. So we better be back to the same condition we were when you were standing on the ground. So tension on the liver organs, liver ligaments is equal to the mass of the liver times G. So I've only heard about this. So Ariana and Marissa, can you tell me if this is real? Once you reach terminal velocity, do you feel a little bit less funny in your belly? Yeah. So it's kind of strange that in some ways it's more comfortable once you reach terminal velocity. On the other hand, the ground is speeding up at you, and I would think that's a little hair-raising. This has an interesting consequence for cats. So there is a study done by a group of vets in New York City where people over time bring cats that have accidentally fallen out of their apartment building windows. So cats, you know, they like to sun themselves in the windowsill, and sometimes, unfortunately, they do fall out. Cats are pretty good at falling. So basically, if they fall from 1 story up, they will never be injured. There's no problem with that. When they fall from 2 or 3 or 4 or 5 stories, as you might expect, the higher they fall from, the more severe the injuries are. But then something strange starts to happen at around 6 or 7 stories. If you go 7 to 8 to 9 to 10, the injuries start getting less severe. And in fact, if a cat falls from a window that's 15 or more stories high, they almost never have any severe injuries. Quite surprising. So we don't really know why, because nobody has gotten video of the cats falling, but the theory is once the cats reach terminal velocity, they relax. And being relaxed is a better way to be in a collision. My dad was an ambulance driver, and he was really disgusted by drunk drivers because they cause so many accidents, and especially when he was working back in the 60s and 70s, it was a much worse problem than it is now. And one of the things that sort of disgusted him is that most of the time they were almost uninjured because they were so relaxed in the collision, whereas the person that they'd hit often was very badly injured. So being relaxed is a better way to survive a collision because you don't have, you know, all your muscles tense. It causes your bones to break. And also the theory is when they relax more because they're feeling they're at terminal velocity, they feel like they're on the ground, they will tend to let their arms and legs spread out more, which reduces their terminal velocity still further. So quite a surprising result. Okay, so that's terminal velocity, and we'll see why that's important probably next time. But for now, we are going to talk about diffusion, random walks, and uncorrelated random numbers. So we're going to draw together a bunch of things from different fields, mathematics, physics, biology. They're all tied together by this one fairly simple idea that is just tremendously important. So let's couch our discussion in terms of the following situation. Let's say an O2 molecule needs to diffuse through cell membrane, or needs to move through a cell membrane. So this is essential to the support of life. Oxygen has got to get into your cells. the way it does it is by a process called diffusion, which involves a random motion. So we know that the oxygen molecule is moving because it has some thermal energy associated with its translation. But if it's inside of a cell membrane, it doesn't move very far at all before it hits something. And when it hits something, it's going to rebound off of that and move in some new direction. It hits something else, moves here, hits something else, moves here, hits something else, moves here, hits something else, moves there. It looks like it's moving more or less randomly, and it is basically moving randomly. So we can model this with what's called a random walk. So each step is in a random direction. And as we often do in physics, we're going to start with the simplest case, and then next time we'll generalize. So we're going to start with a one-dimensional random walk. So let's say here's the oxygen molecule. First, maybe it takes a step to the right, and then a step to the left, and we can allow these steps to have different sizes. There's going to be some peak, some most common size, but there's a range of different sizes, and sometimes it's moving left, sometimes it's moving right. So we're going to say there's an average step size of d, and steps to the right or left are equally likely. And so let's say that the molecule starts at x equals 0. And we ask the question, after 2 steps, what is the average value of x? So we're going to repeat this experiment many, many times on many different oxygen molecules. Again, they're only moving in one dimension. We let them go for 2 steps, and we ask, what's their average position? So we can sort of talk in terms of the average step size of d. And so if we think just about taking average size steps, there are basically 4 possibilities for these 2 steps. So we could have both steps go to the right. We could have both steps go to the left. We could have the first step go right and the second step go left, or the first step go left and the second step go right. If I take the average of those 4, which will occur with equal frequency, what's the average final x? Allison?
0.
0. X average equals 0. So we can see from this that when you're talking about a random walk, thinking about the average final x does not tell you very much. On the other hand, if we ask about what is the average distance from the origin, we can see that that's non-zero, because here we've got 2 units of average distance away from the origin. This one also has 2. This is 0, this is 0. So the average distance from the origin would be 1. And so we can see the random walk did something in terms of moving away from the origin on average, but it didn't do anything in terms of moving your coordinate. So to characterize the average distance, and we don't care about whether it's plus or minus, from the origin, we use the mathematical trick that when you square a negative number, you get a positive number. And so we're going to square all the displacements. And then we'll take the average of those squares, but we want to think about the average distance, so then we're going to take the square root of that. So this is kind of a standard thing in science, which is called the RMS displacement. You'll encounter this in all kinds of different areas of science, where the RMS stands for the root, the R of the mean, M of the square S. So let's apply this to our example here, and you'll see a little bit more what I mean. So example, let's do it, apply to one step, and let's calculate what the RMS value of X is after one step. So it's the root, meaning the square root of the mean, and we're going to use the angle brackets to be the mean, meaning the average of many trials and or many oxygen molecules of the square. And so this is going to be, we could call it, it's a plus or minus D, because you're taking a step to the right or to the left by D, but then we're squaring that. Because we square it, it doesn't matter whether it's plus D or minus D. Taking either of those and squaring it, you get D squared. So this is the square root of the average of D squared. And D already has the average built into it, so it's just D. So the result of taking one step in random walk gives you an RMS displacement of one step length. So far, this should not be surprising. Now let's try it for two steps. So XRMS would be the square root of the average of, let's call it D1 is the displacement for the first step, and D2 is the displacement for the second step. So we take those two steps, add them together, and then square it. So D1 could be plus or minus D, and D2 could be plus or minus D. Okay, so let's multiply that out. So this is the square root of the average of foiling it out. We get D1 squared plus 2 D1 D2 plus D2 squared. Average square root. Now that 2D1 D2, there are four possibilities for it. We might have D1 equals D2 equals plus D. In that case, 2D1 D2 is just 2D squared. Or we could have D1 equals D2 equals minus D, and then 2D1 D2 again is 2D squared. Or we might have D1 equals plus D and D2 equals minus D. In that case, 2D1 D2 would be minus 2D squared. Or we could have D1 equals minus D and D2 equals D, and then 2D1 D2 equals minus 2D squared again. So it's a basic principle of probability that each of these four possibilities is equally likely. And so when we take the average of 2D1 D2, we've got two components that are plus 2D squared and two that are minus 2D squared, so the average would be 0. So that means that XRMS is just the square root of the average of D1 squared plus D2 squared. Each of those on average is just D squared, so that's the square root of 2D squared, which is root 2 times D. Now notice this first one, for one step, which was up here, we got just D. I could write that as the square root of 1, the number of steps, times D. So we're starting to see a pattern. that maybe X RMS is the square root of the number of steps times D. Let's just push it one more step. We'll do 3 steps. So in that case, X RMS equals square root of the average of D1 plus D2 plus D3, all that squared. And again, each one of those could be plus or minus D on average. So let's multiply that out. Square root of the average of D1 plus D2 plus D3 times D1 plus D2 plus D3. Average square root. So let's multiply this out. This is the square root of the average of, I'm going to multiply D1 times each of these 3 terms. So D1, D2, and D3. So I'm going to get D1 squared plus D1, D2 plus D1, D3. Then I'll multiply D2 times each of these terms. So that's going to be plus D2, D1 plus D2 squared plus D2, D3. And then finally I have D3, D1 plus D3, D2 plus D3 squared. Each one of these cross terms on average will be equal to 0, just like what we saw before for the D1, D2, right? So half the time D3 and D1 are going to be the same sign, half the time they'll be opposite signs. And so on average, you're going to get 0 for each one of those cross terms. So putting this all together, this is the square root of the average of just D1 squared plus D2 squared plus D3 squared. So that's the square root of 3D squared, which is root 3D. So this is not exactly a rigorous mathematical proof, but I think you can see the pattern. So in general, X RMS is equal to the square root of the number of steps, capital N, times the average step size. And that's sort of our pretty big, important result. So we'll give that 2 stars. Questions so far? Okay. I'm kind of talking a lot today, but that's sort of the kind of day that it is. So my apologies. So let's apply this equation. So many different places in science that it's important, but we'll review 3 of them in particular. One is signal averaging. So this is an idea that's important to any scientist, whether you're a physicist, chemist, biologist, psychologist, whatever it is you're doing. If you're doing science, signal averaging is a really important idea to you. And what I mean by signal averaging is the idea that when you're trying to measure something, if you're trying to measure it precisely, you would repeat the experiment many times and take the average of those experiments. So repeating experiment and taking the average. So let's see how that works mathematically. And I want to sort of draw that process graphically. Let's say we're plotting on the vertical axis X, which is called the signal. This is what you're measuring. And it might be the mass of something, or the length, or the speed, or the action rate, whatever it is that you're measuring. You get a number, we can plot it, and we're plotting it as a function of time because maybe you're just monitoring the signal continuously, or maybe you're repeating the experiment. So anyway, there's always going to be some noise like this. So there's always some fluctuations about the average value X naught. And that's what you want to know. You want to know this intrinsic real value X naught, but there's always things that are causing noise in your experiment. Sometimes it's your instruments that always have some noise in them. Sometimes it's something intrinsic in your system because there are thermal fluctuations in your system, for example. Sometimes it's interference from sources outside your experiment. Whatever, there's always stuff that causes noise. So we're going to symbolize each experiment by a data point here. So let's say maybe here's experiment 1, experiment 2, experiment 3, experiment 4. You take it each one at a different point in time. And let's say for this one here, the X that we measure for that particular experiment, I could write as the desired average value plus some displacement away from the average, delta X, which is caused by the noise and interference. We don't know how much that is. We just get X. What we want to know is X naught. We can define the signal to noise ratio. So S over N. So it's a ratio of the signal to the noise. For one measurement would just be X naught over delta X. So now let's think about what happens when we repeat the experiment many times and take the average. For average of many repetitions, we would have that X average is equal to the result for measurement 1, X1 plus measurement 2, etc., divided by the number of measurements, capital N, number of repetitions of the experiment. And so each one of these, so X1 is X naught plus delta X1, X2 is X naught plus delta X2. So each one of them we can think of as the desired actual value X naught plus some fluctuation away from that, which could be a positive or a negative fluctuation. So using that, I can rewrite that X av equals X1 plus delta X1, X naught plus delta X1 plus X naught plus delta X2, etc., divided by N. So I can factor out the common X naught values. So there are N of them. So it's N X naught plus delta X1 plus delta X2, etc. Now these delta X's, some of them are positive, like the one I showed in red here. Some of them are negative, like let's say this one. So it's just like a random walk where you're taking some positive steps, some negative steps, and you're adding them all together. So this is a random walk. And so on average, this will be equal so the average value of X av would then be, so this first part, NX naught over N, that just becomes X naught plus the square root of N times the typical deviation. So this is sort of the average error for a single measurement, which in this version of the random walk, we're saying that average error, you can think of that as the average step size of a random walk. And then use this equation that we had from before, that XRMS is square root of N times the average step size. So now let's calculate the signal to noise. It would be X naught divided by, I'm sorry, I made a little mistake. This should be over N, right? Because it was random walk divided by N. So let's just simplify this one more step. So this will be x naught plus delta x divided by square root of n. So I'm canceling a square root of n between the top and the bottom. So the signal to noise would be x naught divided by delta x over root n, which is equal to root n times x naught over delta x. When we recognize x naught over delta x, that's the signal to noise for one repetition. So we did improve our signal to noise, as you should have expected, but maybe we didn't improve it by as much as we wanted to, because it only improves by the square root of the number of repetitions. So this means, for example, that if you need to improve your signal to noise by a factor of 10, you're going to have to do 100 repetitions of the experiment. So sometimes that's what you got to do. That's sometimes life as an experimentalist. To get publishable data, you might have to repeat your experiment a lot. Hopefully you can design your experiment so it can be repeated automatically and just leave it running overnight or something like that to get a bunch of reps. Questions? Okay, I think that's a pretty good place for us to pause for today. Thank you.